So hopefully that's something that you can utilize. The second page is more what we are doing concurrently. So the second page talks about a relative extrema occurring at critical numbers. So I know that in calc right now, like I'm using words you really haven't had in your vocabulary before. So an extrema is a max or a min. It just encompasses both. And then relative is local or near. And then we call the critical numbers point C. What we've been talking about for the past few days are increasing and decreasing. So if x is less than x2 implies that f of x1 is less than f of x2, etc. So we are going to have these guidelines, and again, this is just introducing and making sure we understand all of that vocab. So I want to go down and I want to look at example number 1 for you. So we've talked a lot about the first derivative test. I want to do an application in terms of an AP worded problem. So this came off a past AP exam. So it said find the points that are the relative extrema of the function on the interval 0 to 2 pi. So it's important to note that the given interval is not closed. It is open. So that's important. We have to find, in order to find our relative extrema, a relative extrema can only occur at a critical point. So we have to find the critical points for our extrema. So that means we need to find the derivative. And then the critical points occur where the derivative is 0 or does not exist. So we're going to find when 1/2 minus cosine x equals 0, and at any point where 1/2 minus cosine x would be undefined. So we have the cosine of x is equal to 1/2. So when does the cosine of x equal 1/2? Well, it equals 1/2 at pi thirds and 5 pi thirds. So since the cosine of x is equal to 1/2 at pi thirds and 5 pi thirds, we need to create our sign chart. Now remember, my sign chart is restricted to the interval 0 to 2 pi. So you don't want to be looking at values beyond those. And then we're looking at pi thirds and 5 pi thirds. So you have to know what points fall between pi thirds and 5 pi thirds, etc. So an easy point is pi halves. We know that pi halves is bigger than 5 pi thirds. And we also know that, smaller than 5 pi thirds, but bigger than pi thirds. And it's an easy value for us to find. So the cosine of pi halves would put us at the top of the unit circle. So the cosine at pi halves is 0. So then you have 1/2 minus 0, which is 1/2, which tells me that we are positive between pi thirds and 5 pi thirds. And then thinking about the cosine and thinking about a value less than pi thirds. So that would be like looking at pi 6 or pi fourths. We know that the cosine of pi fourths is square root of 2 over 2. So you do 1/2 minus root 2 over 2 and 1 minus the square root of 2. Well, 1 minus the square root of 2 is going to be negative because the square root of 2 is greater than 1. So that means that it is negative between 0 and pi thirds. and then picking a number greater than 5/3 but smaller than 2 pi. So again, 5/3 isn't, it's pretty close to our endpoint there. So you'd have to pick a unit circle value just beyond that, which would be like 11 pi 6. So the cosine of 11 pi over 6 would once again kind of be like the cosine of pi 6, but it's in quadrant 4, so it's positive. Root 3 over 2. So 1/2 minus root 3 over 2 is like 1 minus root 3, which is negative. So negative over positive gives you a negative. So we have negative, positive, negative, which tells me that my original function is decreasing from 0 to 5/3 and 5/3 to 2 pi, and increasing from 5/3 to 5/5, which means that there is a relative min at x equals 5/3 and a relative max at x equals 5/5. And my justification is because of the change in signs on the derivative. So you could say f of x has a relative, and then you'd pick min or max. If I pick min, I would say f of x has a relative min at x equals 5/3 because f prime of x changes from negative to positive. And then you could just flip it for your second part, and you could say that f of x has a relative max at x equals 5/5 because f prime of x changes from positive to negative. Okay, find the points that are relative extrema for the function f of x equals x squared minus 4 to the 2/3. So once again, same idea. I'm finding my derivative, and I saw we struggled with finding the derivative for a square root earlier, so I wanted to make sure we walked through one now. So even though this is cubic, the idea or concept is the same. The exponent comes down, you subtract 1 away, and then you multiply by the derivative of the inside. So my derivative becomes 4x over 3 to the cube root of x squared minus 4. So my critical points are when 4x equals 0, and when 3 cube roots of x squared minus 4 equals 0. So that means I have a critical point at x equals 0. Dividing both sides by 3, they kind of cancel out. And then you have to cube both sides. And we get x squared minus 4 equals 0. Which means my critical points occur when x is equal to plus or minus 2, as well as when x equals 0. So to find the relative extrema, I have to look for the sign changes surrounding -2, 0, and 2. So plugging in something like -3, we get a negative on top. -3 squared is 9. So 9 minus 4 is 5. The cube root of 5 is going to be positive. times 3 is positive, so a negative divided by a positive is negative. So this graph is negative to the left of negative 2. Plugging in negative 1 gives me a negative on top. And 1 minus 4 gives negative. The cube root of a negative is negative. So a negative divided by a negative is a positive. Now for all values greater than 0, my numerator is positive. It's really just going to depend on the sign of the denominator. So if you plug in 1, 1 squared is 1, 1 minus 4 is negative. A positive divided by a negative gives a negative. And then if you plug in something bigger than 2, you're going to always have a positive on top and bottom. So when it asks you to find the points that are relative extrema, it goes decrease, increase, decrease, increase. So I have 3 relative extrema. I have local mins at x equals negative 2 and x equals 2. So f of x has local mins at negative 2 and 2 because f prime of x changes from negative to positive. And then f of x has a local max at x equals 0 because f prime of x changes from positive to negative. So again, we always talk about what we know. We know the sign changes, therefore we know those are local maxes and local mins. That is what the first derivative test told us. So that was like 4.3 day 1. The candidates test is like the extreme value theorem added to the first derivative test. Because now I can find these absolutes because I have endpoints. So a closed interval changes how I look at my problems. A closed interval changes how I look at my problems because now I have endpoints. So now when I look at example A, I have to find f prime of x. So I have f prime of x equals 12x cubed minus 12x squared. So I can take out a 12x squared, leaving me with x minus 1. So that makes my critical points at 0 and 1. So the candidates test now says not only do I have to check my critical points, but I have to check the endpoints for my extrema. So if it asks me to find an absolute extrema, I need to take the critical points and my endpoints. So negative 1, 0, 1, and 2. And I need to find the f of x values. So we're finding the f of x by plugging back into the original. So negative 1 plugged back into the original gives 3 minus 4 times negative 1. So that's really like 3 plus 4, which is 7. 0 cubed and fourth is always 0. Plugging in 1, 3 minus 4 is -1. And plugging in 2, well, 2 is a little more complicated. 2 to the fourth is 16. 16 times 3 is 48. 2 cubed is 8. 8 times 4 is 32. So 48 minus 32 is 16. So from the candidates test, I have an absolute max at 2. And I have an absolute min at 1. If we did our first derivative test, you would need to do the first derivative test to determine if 0, 0 is a local. So we didn't perform the first derivative test, but we would need to determine if, so it's to be determined if the first derivative test says that's a local. But again, it only asked me for the absolute, so I'm not wasting my time finding the local. Do we see the difference between the two? Okay. So I just want to make sure all of that vocab is clear. That's kind of why I threw this package sorted together, just to walk through that. The next part is concavity. That's what we've been focusing on kind of more recently, talking about concave up, concave down, points of inflection. With the chair delay, I don't have time to do every example with you. So that's why I'm kind of going quicker and jumping over examples. So we have determined the open intervals on which a graph is concave up. State those points of inflection. So for this example here, we have x to the fourth minus 4x cubed. So we have to find the first derivative and the second derivative. So we have 12x squared minus 24x. For concavity and POIs, I only care about that second derivative and its zeros. So that gives 12x times x minus 2, which gives me x equals 0 and x equals 2. This is an open interval, which means my concave up, concave down are going to have infinities. Plugging in -1, 12 times -1 is negative. -1 minus 2 is negative. 2 negatives make a positive. So it's concave up from negative infinity to 0. Plugging in 1, positive, negative. A positive times a negative is a negative. So from 0 to 2, it's concave down. And then plugging in a number bigger than 2, like 3, will give a positive times a positive. So it is concave up from 2 to infinity, which means I have 2 points of inflection. I have a point of inflection at x equals 0 and x equals 2. And our justification for each one depends on here. So you can say x equals 0 is a POI on f of x, because f double prime of x changes from positive to negative. And then you'd say something similar for x equals 2, but you would have to talk about how it goes from negative to positive. Tomorrow, we're going to have a live lesson on the next stuff. I did, because I was so upset about that table the other day and how AP had it wrong, come up with another table, but because we're down to about 2 minutes, we don't have time to work through that. I'm actually going to just work through that second concavity example, but I want to touch on the fact that your homework's for tonight would be that 4.3 homework day 4. So it's like 12-ish questions. It's those next 2 pages. So it's the 1 through 4, but then it jumps, or actually it goes 1 through 8, and then it goes 1, 2, I skipped 3, 4, and then I jumped all the way to 9 and 12. So I like kind of cut and paste a couple worksheets together, kind of putting this together for you today. But if you want to see example 6, because this has a fraction, or example B rather, because of that fraction, I'm going to quickly kind of do that for you, because I keep seeing us having issues with quotient rules. So it's ho d high minus high d ho all over ho ho. The beginning part cancels out. So you get negative 12x over x squared plus 3 squared. If you don't like the quotient rule, you could bring that squared up as a negative 2. And then your second derivative would be but once again, each term has an x squared plus 3. So you can cancel each of those out. Negative times a negative is a positive. So that's going to simplify to negative 12 times x squared plus 3. And then 2 times 12 is 24x squared. Actually, JK, there's another 2 in there, so I'm going to turn it to 48x squared. And that middle term is gone. All over x squared plus 3 cubed. Distributing that negative 12. You use top and bottom to find your critical points. So 48 minus 12 actually gets me to 36x squared. So then you have a 36 here. So I'd factor my 36 out, leaving me with x squared minus 1. So that makes my critical points there, x equals plus or minus 1. And then my denominators, if you cube root 0, you get 0. And then we get that equal to a negative, so that's i's. So those are non-real, so they don't matter. So my only critical points are negative 1 and positive 1. So when you did your number line, those would be your critical points. I know I kind of worked through that rather quickly, but I hope that helps you with your quotient rules. Yes?
So our homework's these next 2 pages?
Yes. And then tomorrow during class, I'm going to do all those graphing examples with you, as well as the table. So I will be live at 8:35 tomorrow morning, and I will be starting at 8:30 or whatever. I think class is actually at 8:31, but I will not be admitting anybody late, so be on time.